Okay, who are you? Who is this?
It's me,
Who's me?
Donovan.
Okay, Donovan. The reason you're in there is Candace Gully. So
Oh,
uh, basically, that's part of the reason why I have to let you in. It's because I don't know if you remember, there was a hacker. There was like a professional hacker that got busted, and when he got put before the judge, they had a Zoom meeting like this, and they had pornography going on in the courtroom hearing.
oh,
So that's why I have to kind of screen everybody that comes in here.
okay.
No problem. Ali, did you get my? She's still looking up. Mila, how you doing, Mila?
Good, I'm just eating some chicken nuggets.
It was not my finest hour. I've had better teaching than that last thing.
Listen, it was not mine either. As kids were driving me nuts. I'm like, let's go lay in your bed and you guys can calm down. And then I'm like falling asleep. I'm like, oh God.
Yeah, it's to be honest with you, I don't even know if it's worth viewing that video again. And it's I'll be honest with you. I
will say I actually understood it, but it's more for me. It's more math. I can kind of put that together a lot easier than regular chemistry. So
I came out. My chest was really puffed after Tuesday because I'm there, and it seemed like everybody understood what was going on. And then today, it's like I can't put two sentences together that make sense.
Yeah, well, it happens sometime. How have you been feeling?
I was really, really tired before I started today, so that might have something to do with it.
Probably. Yeah.
Allie, did you get my email?
I did.
I'm sorry to be so depressing, but I'll be honest with you. I'm surprised you're doing this well without algebra.
Yeah, I don't know. My wife laughs at me. I took math for liberal arts when I started my undergrad, but that was back in 2006. I don't know. I did social sciences for my degree. So
I'm amazed you're being able to do as much as you are in chemistry, having not had algebra yet.
Yeah. Well, it's a new world with YouTube videos. I have to say, there's a lot out there that makes teaching a lot different.
And again, I have to be honest with you. I always advise people, never take chemistry and a math, never take chemistry and physics, never take physics in a math class in the summer. It's okay because it kind of gets diluted out over an entire fall or spring semester.
Yeah.
But when you're taking two technical subjects,
it's draining.
Literally speaking, you would not have a life at all.
That's literally, I'm in calculus with geometry and with you. And I feel like those are my only two classes that I have because everything else is like, just so quick, get it done. And then like you guys, I'm like, focus, do the notes and get everything done.
And Allie, she's taking it over a 16-week semester as opposed to a 10.
It's awful. It's so
yeah, I don't know what to tell you, Allie. The only thing I can tell you, always take what the advisors tell you with a grain of salt.
Mm-hmm.
I have never been impressed with the advisors at SPC. Never.
Yeah.
Because you have to understand, I deal with their mistakes. Yeah, Allie, you've got enough gumption that you're going to go out and see, you're going to go out and learn algebra on your own to succeed in chemistry, right? You have been doing that. All right. There are other people that don't. They assume that the advisor knows everything, and
Mhm.
algebra, you don't need algebra to take chemistry.
I'm surprised it's not a prereq for the class.
I thought it
I
was.
think it is, but I don't know how I got into this one.
I don't, genuinely, I don't think they really follow the prereqs that are required for it.
Except when I went to go sign up for general, and then it was like blocked. You can't do it without math and this class.
Take it, please, Ellie, take it step by step. Okay?
Yeah.
You'll academically, you'll learn more, and you'll have much greater success doing it that way.
Yeah,
than
it's hard.
trying to bunch everything at once.
It's hard. I stay up till like 3 a.m. every night, just trying to do homework and studying and stuff. And then I'm up again at like 6 with the kids. So yeah, it's a lot.
Gosh.
Okay, again, let's see who else is in there. Lewis, Neela, Mariah. Guys, I apologize. I had a bad day teaching in lecture. What can I say? I was so happy from Tuesday. Everybody seemed to be getting it. And I'm like, oh, I'm the greatest teacher ever. And I'll pat myself on the back. Great. Yay, Greg. Yay, Greg. Every now and again, you get a humbling experience like this. So I apologize. I'll try and pick it up on Tuesday. Okay, guys. Kaylin,
Hello.
not my finest hour in lecture. I apologize.
That's okay. You're
Uh,
recovered.
I will get it. We'll try and get it more succinct on Tuesday.
Okay.
All right, ladies and gentlemen, I think it's about time anyway. I got 11 of you in here, and I'm supposed to have how many? Wednesday, Thursday. I'm supposed to have about 22 of you in here. And I got half. Okay. They are going to be surprised because this is not an easy, this is probably one of your last hard labs left. Next week, believe it or not, I have no idea why they schedule things the way they do, but I believe next week is the mole lecture. Am I wrong? I thought I saw that. Kaylin's like, I don't care.
I thought we just did moles. Am I losing it?
I may be losing it.
I think next week's dimensional analysis.
Yeah, okay. I
That
knew
one.
it was something stupid.
Yeah, some from week 1.
Yeah, we've did dimensional analysis way, way, way back. Why in the world we're doing it now is beyond me.
It's
But-
like we know you.
But we have dimensional analysis next week. And keep in mind, there is another extra credit assignment next week. Okay? So this one is going to be a hard one though. So I'm going to get out of here, hopefully. Hi, Marie. Not my finest hour in lecture. I apologize.
No, that's okay.
Just had a bad day. What can I say? All right, guys, I'm going to go through and I'm going to talk about, it's going to be a good review for the people that have my lecture. For other people, if you've had empirical formulas, great. If you haven't, well, we're going to go through some of the simpler formulas, all right? By show of hands, who has not had some sort of empirical formula lecture yet? Do not dare raise your hand, Kaylin. Don't raise your hand, Kaylin. Donovan, you had it? Have you had empirical formula?
No.
You haven't had it yet.
No.
Allie,
Yes, we just covered it.
just covered it, okay? Let's see. Okay. I'm looking through to see. Michael, have you had it yet? Michael, have you had empirical formulas yet?
We talked about it for like 20 minutes.
Okay, well, we're going to talk about it for a little longer tonight. Sheridan, have you had it yet?
I don't think so, no.
All right. All right. That gives me a basis to start. I apologize to those of you that may be bored by this, but we're going to go from kind of the beginning of this. So when we're going to be talking about two different types of problems tonight. The first half are going to be percent composition or mass percent composition. The second half are going to be empirical formulas. Mass percent composition. It's very easy, guys. It's really, really not that hard. All you got to do is take the part, divide it by the whole. Doing nothing more than doing percentages. That's all we're doing. I got a mixture of copper and sulfur. The copper mass is 3.45 and the mass of the mixture is 9.42. What is the percent copper?
Out.
Okay. Donovan,
Yes.
I want to know the percent copper. So the percent copper is going to go on the top of my fraction.
Okay.
The whole is going to go on the bottom. So Donovan,
Okay.
what number goes on top? What number goes on the bottom?
The whole goes on the bottom and part on top. Is that what you said?
That's what I'm saying.
Mm-hmm.
So I've got a screen open here. I've got a weight of copper and I got a weight of copper and sulfur. Which number goes on top?
Would 9.42 go on the bottom?
9.42 is
yeah.
the whole weight. That goes in the bottom. What number goes on top, Donovan?
3.45.
So I take the 3.45, divide it by 9.42, and multiply by 100. I have 36.6% copper. Pretty straightforward, guys.
Yeah.
Now I have a second problem. I got a mixture of sand and iron. The sand and iron weighs 20.56 grams. What I do is I weigh a magnet. The magnet weighs 35.27 grams. I then pass the magnet over the sand iron mixture. Iron clings to the magnet. I then reweigh the magnet. It weighs 42.83 grams. What is the percent iron in the original mixture? So I got to figure out the part over the whole. Looking at the problem, do I know what the whole is right off the bat? Allie, what is the whole weight?
20.56.
20.56 is the whole weight. Now, Allie, can you figure out how you're going to get the weight of the iron?
Would we use the 42.83 and then subtract the 35.27 to get the weight of the iron?
Exactly. The 42.83 is magnet plus iron. Magnet weighs 35.27, so I'm going to subtract the 2. I subtract the 2, I get 7.56 grams. I divide that by the whole weight mixture and multiply by 100. I get 36.77% iron in that mixture. We are on solid ground here, guys? Anybody confused at all at this point? Okay. Mass percent using chemical formulas. Now, I have a chemical formula, Na2Cr2O7. We have to remember, mass percents are part divided by the whole. Now, I have atomic weights for each one of these elements. and I know the subscript of each one of the elements within the formula. So I can figure out what sodium's contribution is by simply taking the subscript number and multiplying it by the atomic weight. I get that sodium's contribution is 45.98. I get a 2 for chromium too. Chromium's atomic weight is 52, so its contribution is 104. I have 7 oxygen atoms. Each one of those weighs 16, so 7 times 16 is 112. I add up all the contributions, and the whole molecular weight of sodium dichromate is 261.98 grams. Now, trying to figure out somebody's hiding on me. Michael. Michael?
Yes.
All right. If I wanted to know the percentage sodium, do I have sodium's contribution to the molecular weight?
Yes.
Do I have the molecular weight?
Yes.
So do I have a part over a whole?
Correct.
So how am I going to get the percentage of sodium within that molecule?
45.98 divided by 261.98 times 100.
Absolutely. Marie, how am I going to get chromium? Just give me the numbers, Marie.
Oh,
Percentage of chromium with these numbers, Marie.
oh, the contribution of chromate is 104.00 divided by 261.98.
Absolutely.
100.
Mila.
Me?
Yep, you.
Okay.
Yeah.
I
Cheer
got
on,
the crew here.
cheer on mom, okay? Okay, Mila. What is the percentage of oxygen looking at this screen? Tell me how to figure that out.
Wouldn't we take the contribution by the total?
Tell me the numbers.
Okay, you take the 261.98 and then divide it by the 112.
Other way around. The part
Other
goes
way
over the
around.
whole.
Yeah, then the 112 divided by the 261.98.
Okay.
I'm
So,
sorry.
no. So that's all we have to do. And you know, the amazing thing, guys, all we have to have is the chemical formula. And we know any weight of sodium dichromate. Pick a number. Donovan, pick a number for me. Any number at all. Donovan?
My bad, I was on mute.
Pick a number. Any number.
17.55.
No. Don't use one of these. Just pick a number other than one of the
Oh,
ones
in my
on-
head, 15.
15. So Donovan, isn't 17.55% of 15 going to be the percentage of sodium? If I have 15 grams of sodium dichromate, isn't 17.55% of that 15 going to be the grams of sodium?
Yes.
Isn't 39.70% of that 15 going to be my grams of chromium?
Yes.
And isn't 42.75% of that 15 going to be my grams of oxygen? So this is a tool, guys. If we have an empirical formula, you know what the percentage of each element is within that formula, and you can apply it to any weight. Another problem here. I weigh a sample of silver. It weighs 42.87 grams. I heat the sample, all the oxygen was driven off. And I reweighed the sample, and it reweighed at 39.91. What is the percentage of oxygen in my silver oxide? You got to realize that the compound is made of only silver and oxygen. If all of the oxygen was driven off, only thing left is silver. So, help me out here, Neela.
Yes, I'm sorry.
Is it not Neela? Nyla.
Okay, thank God, because I was not listening to anything you said. I'm sorry.
Okay, I'm here.
Not that it was important, Mila, but that's okay.
They're fighting over motorcycles, so we're good.
Nyla.
Yes, I'm here.
All right. So we have this problem before you, and I want to know the percentage of oxygen. So I got to get the part. The part is the weight of the oxygen. How am I going to get the weight of oxygen here?
I'm sorry, hold on. I'm just reading the problem over.
Ah, somebody wasn't paying attention.
I mean, I was, but reading it better. Oh, don't you subtract how much you got, how much silver oxide you got from what you're weighted?
So I'm just going to subtract the 39.91 is the weight of the silver. All I got to do is subtract that from the weight of the silver oxide. If I can ever get the screen to move. Subtract the silver from the silver oxide. That gives me the weight of the oxygen. Now, Nyla,
Yes.
what am I going to divide it by? The weight of the silver oxide or the weight of the silver?
The weight of the silver oxide.
That's the weight of the whole thing. So I'm going to take the 2.96, divide it by the 42.87. That will give me the weight of oxygen in my silver oxide. Questions, ladies and gentlemen? Okay, so those are the kind of problems we're going to do with mass percent. Now, we got to look at empirical formula problems. That's the second type of problem we're going to be doing tonight. And Allie,
Yes.
I have 1 molecule of sodium phosphate. Do you see the screen before you?
Yes.
If I have 1 molecule of sodium phosphate, how many atoms of sodium do I have?
3,
Phosphorus?
4, or
Phosphorus
1. Sorry, 1,
and oxygen.
4.
All right, absolutely perfect. Now, say I want to multiply that molecule so that I have 6.02 e to the 23rd molecules. How many sodium atoms do I have? If 1 molecule gave you 3 atoms,
Okay.
then 6.02 times 10 to the 23rd molecules, doesn't it give
Multiplied
you?
by 3.
You multiply by 3 to get 1.8 e to the 23rd. Phosphorus, it's a 1-to-1 relationship. So if I have 6.02 e to the 23rd molecules, I have that many atoms of phosphorus. And since there are 4 oxygens, I got to multiply 4 times that number.
Mhm.
But you got to remember, 6.02 times 10 to the 23rd is 1 mole. So if I divide the 6.02 times 10 to the 23rd by that same number, that means I have 1 mole's worth of sodium phosphate. I divide the 1.81 e to the 23rd by 6.02. That gives me 3 moles of sodium. I divide it into the 6.02. That gives me 1 mole of phosphorus. Similarly, this will give me 4 moles of oxygen. So in effect, can you see? The subscripts are nothing more than the molar ratios of the atoms within the molecule. Does that make sense? Every time you see subscripts within a compound, the subscripts are the molar ratios of the atoms within that compound. If I have something like this compound, That means I have a molar ratio of 6 carbons to 12 hydrogens to 6 oxygens. If I want to reduce that down to its simplest form, there's a ratio of 1 mole of carbon to 2 moles of hydrogen to 1 mole of oxygen. Does that not make sense to somebody? Does everybody understand what I'm just saying now? Subscripts are the molar ratio of the atoms within the molecule. So when we're doing empirical formula problems, there are 4 steps. The first one, get the masses of all the elements in the formula. Generally speaking, this is going to be your hardest step. Next step, turn all the masses into moles by multiplying by 1 mole over the atomic weight. Then you're going to have a list of moles. You're going to find in that list the one that's the smallest. And you're going to divide it and all the others by the smallest number of moles. That will give you the molar ratio. Now, has anybody ever seen a chemical formula with a fraction of an atom? You can't have half an atom. Can't have a third of an atom. So if your molar ratio does have a fraction in it, you have to multiply it by a whole number to get it to be a whole number. Like, for example, if you have a molar ratio of 1 to 1.5, you got to multiply the 1.5 by 2 to get a whole number 3. But in order to maintain the molar ratio, if you multiply one of those numbers by 2, you got to multiply the other one. So you have the molar ratio of 1 to 1.5. That's the same as the molar ratio of 2 to 3. And you have to use the 2 to 3 one because that's the one that has whole numbers as atoms. We're going to go through a couple examples so that you'll be able to see what's going on with these. A compound of sodium sulfide has 32.9 grams of sodium, 23.1 grams of sulfur. What is the empirical formula? Step 1 is given to you. You have the grams. Step 2, turn them into moles. I take my sodium grams, multiply it by 1 mole over the atomic weight. That gives me 1.43 moles of sodium. I take my sulfur and multiply its weight by 1 mole over 32.06 grams. This gives me 0.720 moles of sulfur. Now, Donovan,
Yes.
All right, our first step was find the grams. Second step, find the moles. Our third step is find the smallest number of moles and divide it into all the other moles.
Mm-hmm.
Which one's smaller, Donovan? 1.43 or 0.720?
0.720.
So I'm going to divide the 1.43 by 0.720. That gives me 1.99, which is close enough to 2. I divide my 0.720 by 0.720. That gives me 1. So my molar ratio is 2 to 1. And guys, these are the subscripts I then apply to the formula. My ratio is 2 sodiums to 1 sulfur, or an empirical formula of Na2S. Do I have any questions, guys? I'm hearing crickets, so either you've all left the meeting or you're understanding this. I'm going to give you the benefit of the doubt and say you understand it. Another type of problem. Empirical formulas from mass percents. I analyzed the compound and found it to be 26.6% potassium, 35.4% chromium, and 38.1% oxygen. What is the empirical formula? Pick a number. Pick a number, any number.
100.
Well, I'm going to pick 77. So if I say 77, isn't 26.6% of 77 going to be my weight of potassium? Isn't 35.4% of 77 going to be my weight of chromium? And isn't 38.1% of 77 going to be my weight of oxygen? So I do that. This means I have 20.5 grams of potassium. I have 27.3 grams of chromium and 29.3 grams of oxygen. I've got my first step. I got my weights. Now, what's the second step?
Wouldn't it be get the molar mass?
I'm going to get the number of moles from that. So I'm going to take my 20.5 grams of potassium and multiply it by 1 mole over 39.10. I'm going to take my 27.3 grams of chromium, multiply it by 1 mole over 52 to give me 0.525 moles of chromium. I'm going to take my 29.3 grams of oxygen by 1 mole over 16. Now, Sheridan, you out there, Sheridan?
Yes.
Okay, Sheridan. I did my grams. First step's done. Got my moles. Second step. Do you know what you do for the third step?
You divide by the smallest.
Divide by the smallest. So I'm going to take my 0.524 divided by 0.524. That gives me 1. I'm going to take, yeah. Sorry, I'm going to take my 0.525. Let me get out of here for a second because this is disturbing me. I was doing this to illustrate something for my Tuesday lab. And, okay. My 525 divided by 0.524, this gives me 1. 1.83 divided by 0.524, this gives me 3.49, or about 3.5. Now, what number do I multiply 3.5 by to get a whole number?
2.
2. 2 times 3.5 gives me 7. But if I multiply it by the 3.49, I have to also multiply it by the 1 and the 1 again. I do that. That gives me 7 for my oxygen, 2 for my potassium, 2 for my chromium. So my empirical formula is going to be K2Cr2O7. Note, guys, when I originally started this problem, I chose 77. Make it easy on yourself. When you're at this part and you're choosing a number, choose 100. That means you just have less things to calculate. If it's 100 grams, then 26.6 grams is going to be potassium, 35.4 grams is going to be chromium, and 38.1 grams is going to be oxygen. Questions on that problem, guys? Are we good with that? We okay?
Yes.
New problem. 98.3 grams of manganese was put into a container that had an atmosphere of 100% nitrogen. I sparked it, and the resulting product had a mass of 140 grams. What is the empirical formula? First step, I need to find the masses of all the elements. What do you think the product is composed of? Michael?
Yes.
I put manganese into an atmosphere of nitrogen. I spark it, I create a product. What do you think are the elemental components of my product?
Manganese and nitrogen.
Anything else?
No.
No. So my product weighs 140 grams. Assuming, Michael, that my manganese completely reacted. Can you tell me how much nitrogen I have?
Uh, 41.7 grams.
You can read. All right. How'd you get that 41.7 grams?
Well, my smart self just decided to go on my calculator instead of looking at your slide.
Okay, fine. What did you do to get it though?
140 minus 98.3.
The 140 is the weight of manganese and nitrogen. The 98.3 is just the weight of the manganese. So I subtract those two out. I get the weight of just my nitrogen. Now I have the weights. What's the next step once you get the weights?
Divide
Allie?
by. Oh, I'm
Allie?
sorry.
I got the weights. What's the next step that I have to do?
Who did you ask?
You
We need to find the moles.
need to find the moles. So I got 41.7 grams of nitrogen. I multiply that by 1 mole over 14. That gives me 2.98 moles of nitrogen. I got 98.3 grams of manganese. Multiply that by 1 mole over 55 grams. That gives me 1.8 moles of manganese. What do I divide by?
The 1.8 moles.
I do that into 2.98. I get 1.65. I do that into 1.80. I get 1. Now, I got 1.65 to 1. I cannot leave this as a fraction. So what I'm going to do is I'm going to multiply it first by 2. And this gives me, that right?
3.3.
Is that a whole number?
No.
So I got to go to the next number. I'm going to multiply it by 3. And this gives me 4.95. Is that close to a whole number?
Yes.
So I'm going to multiply it by 3 and say that that is about 5. If I do
What's
it to
the-
the one number, I have to do it to the other.
What's the rule of thumb on if it's close enough?
I would say if it's about a tenth away, it's close enough, either high or low. Okay? But if it's a tenth off, Allie, what I would do is I would go back and re-look at your calculations. Okay? So I now have a ratio of 5 to 3. The 5 is my nitrogen. My 3 is my manganese. So I know that my empirical formula is going to be Mn3N5. By the way, guys, I did it all the way out to 10. Okay? What you want is this number to be the smallest possible. Yeah, I can get it real close. Of all these numbers, this actually is the closest one. So that's the one I chose to use. Another type of problem. A compound has an empirical formula of C2H4O. The molecular mass is 132. What is the molecular formula? What you got to think of is How do you get an empirical formula from a molecular one? If I have a molecular formula of C6H6, to get the empirical formula, didn't I divide the subscripts by a common number? In this case, I divided by 6 to get the empirical formula of CH. So if I'm dividing to go from molecular formula to empirical formula, I'm going to have to multiply my empirical formula by a number to get the molecular formula. All right, let's think about this. If I look at my molecular mass, that's going to be, I've got 6 carbons, 6 times 12 is 72. I got 6 hydrogens times 1, that's 6. I have 78 is my molecular weight for benzene. All right. I have CH. 1 carbon for 12, 1 hydrogen for 1, that's 13. Now, if I take my molecular weight and divide it by my empirical formula weight, this will give me an integer. And an integer is a whole number. All I got to do then is take that integer and multiply it by all the subscripts in the empirical formula. That will give me my molecular formula. In this case, I divide the 78 by 13, I get 6. So my empirical formula was C1H1. I got to multiply 6 times the carbon to give me 6 carbons, 6 times the 1 for the hydrogen, 6 hydrogens. I now have my molecular formula. So let's go back to my original problem. I have my empirical formula. I can figure out what my empirical formula mass is. I have 2 carbons. 2 times 12 is 24. 4 hydrogens. 4 times 1 is 4. 4 plus 24 is 28. I got 1 oxygen. 1 times 16 is 16. 16 plus 28 is going to be 44. So my empirical formula weight of C2H4O is 44. But my molecular mass is 132. I divide my molecular mass by my empirical formula, I get 3. So all I do is take this 3, multiply it by all the subscripts in my empirical formula. So I get carbon 2 times 3, carbon 6, hydrogen 4 times 3, hydrogen 12, oxygen 1 times 3, O3. That is my molecular formula. Questions on that? Today's experiment, guys. We're going to clean and dry a crucible, and we're going to weigh the crucible. Then we're going to put about 5 inches of magnesium ribbon into the crucible. We're going to coil it up. We're going to reweigh the crucible and the magnesium. So therefore, we now know what the weight of the magnesium is. We're going to heat it gently. Sometimes smoke appears. If it does appear, just put the lid on, let it calm down, then start heating it again. If smoke appears again, the second time you're trying to heat it, you put the lid on, calm it down, and let it go on. Then once there's no more smoke, you heat the snot out of the crucible for at least 10 minutes. Put the lid on the crucible, let it cool. Then what you're going to do is weigh the crucible and product. Guys, when you see the data for this lab, all you're going to see are 3 triple beam readings. That's the entire data for this lab. So We have three readings: the mass of the crucible. We have, in your case, it's going to be crucible and magnesium. I'm just using aluminum for this example. And the third thing is going to be the weight of the crucible and the product. Now, we have oxygen and we have nitrogen in the air. Oxygen's much more active, so the oxygen reacts with the metal. So in effect, this mass is going to be crucible and oxide. In this case, it's going to be aluminum oxide. So I have three readings. I've got the mass of my aluminum and the mass of my crucible. My mass of my aluminum is going to be my mass of crucible and aluminum minus mass of crucible. I do that subtraction out. I got 0.508 grams of aluminum. The mass of my product is going to be the mass after heating minus the mass of the crucible. So I do that math out. The mass of my product is 0.959 grams. Now, the mass of my product is only aluminum and oxygen. So if I have the weight of my crucible and product and subtract out the weight of my aluminum and crucible, I'm going to get the weight of the oxygen. The other way to do this, if I have the weight of my product and the weight of my aluminum, I can subtract those two. Either way, I'm going to end up with the same answer. I've done the first step of my empirical formula problem. I found the weights. I also need to figure out the mass percent. Mass percent is part over whole times 100. My aluminum weighed 0.508. The product weighed 0.959. I divide the weight of the aluminum by the weight of the product and multiply by 100. I have the weight of my aluminum. Same thing for oxygen. Weight of oxygen divided by weight of product times 100 gives me the mass percent of oxygen. Mass percent is done. All right, for my empirical formula, second step, I have the weights. Second step, turn them into moles. I've got my weight of oxygen. I multiply it by 1 mole over the atomic weight of oxygen to get 0.0282 moles. My aluminum gets divided by 26.98, its atomic weight. So I have 0.0188 moles of aluminum. Third step, divide by the smallest. I divide 0.0282 by 0.0188. I get an answer of 1.5. I divide 188 by 188. I get a 1. I have a fraction. I got to multiply this one by 2. So my oxygen coefficient is going to be 3. My aluminum is 2. So my overall formula, empirical formula, should be Al2O3. Now, guys, I've used aluminum and oxygen in this example. You're going to be doing the same exact thing, only you're going to be using magnesium and oxygen. I'm going to take you through the data, and I'm going to take you through the data and the report. And then we're going to be done. Okay, let me see. Results you get here. As I said, you're just going to get 3 readings of triple beams. First one is the crucible and lid. Second one, crucible lid and magnesium. Third is crucible lid and the magnesium oxide product. So that's where you're going to get your data. Lab report. Again, you're going to have to get the mass of the magnesium. You know what the magnesium in crucible weighs, and you know what the crucible weighs. Subtract the two of them. Mass of the oxygen, you've got the mass of the product in crucible. Subtract out the weight of the crucible and the magnesium. That will give you your mass of oxygen. You got your mass of magnesium. Multiply it by 1 mole over 24.31. Moles of oxygen, you got your mass of oxygen. Multiply that by 1 over 16. Questions on the first question? Mila, they're calming down.
Yeah, we haven't napped today and it's way past bedtime. Plus they're both sick, so hopefully soon they'll
Valium.
go to sleep.
Valium or whiskey?
Yeah, I wish.
Okay, now you have the moles of oxygen and the moles of magnesium. What you're going to do is divide the moles of magnesium by the smaller one, divide the moles of oxygen by the smaller one. Guys, for this question, I want the rough answer. I don't want the answer after you've rounded. I want the rough answer. From this ratio, you're going to write down what the empirical formula of magnesium oxide is. Post-lab questions. From what you know of magnesium and oxygen, do you have an ionic or covalent compound? Don't answer it. If you have an ionic compound, guys, somebody pipe it up. What's the ion for magnesium? What ion does magnesium form?
Cation.
What cation? What's the charge?
2 plus.
2 plus. So guys, this is absurd. I think this is ridiculous. This is how many choices he gives you. So you know it's magnesium 2 plus. Find magnesium 2 plus on this chart. How about oxygen? What's oxygen's charge?
-2.
2 minus. So you're going to find oxygen 2 minus somewhere on here. Now, based on the charges, what do you expect the mole ratio of magnesium to oxygen to be? If magnesium's a +2 and oxygen's a -2, what is the chemical formula?
MgO.
MgO. What's the ratio?
1:1.
1 to 1. So you know the answer to this experiment before you do it. All right, question 8. Question 8 is a question where they give you all the information. What you have to do for this is determine the empirical formula of iron oxide. Question 9, you have manganese oxide, another empirical formula problem. Figure out what the empirical formula of manganese oxide is. And guys, I've always felt that this is foolish. You got to figure out 2 reasons why your experiment could have screwed up. And if it screwed up, how did it affect your results? All right. Write this down. Write this down somewhere. Your error is you did not heat the magnesium up enough. You did not heat the magnesium up enough. So therefore, your empirical formula is off. Is it off high? Is your ratio of magnesium to oxygen too high, or is it too low? You're right, Mila.
I can't reach the mute, so that was just easier.
All right. Again, the question is, you did not heat the magnesium long enough, so there is magnesium element left. Would that affect your results by having your magnesium to oxygen ratio be too high? Or would your magnesium to oxygen level be too low? Explain why. That's it, guys. Any questions on this? Thank you for bearing with me. I needed to redeem myself after my lecture today. I really did want to give you either a review for those of you that already had it, or at least a good introduction to this type of problem, because it is going to be the hardest one you deal with this semester. Anybody have any questions for me? If that's all, then I hear a Budweiser calling to me.
Have a nice weekend.
Have a nice weekend, guys. Any
Bye.
questions?
Nice weekend.
Bye.
But thank you.
Bye.
Bye.